Right. Well, I think it's time for us to get started. So thank you for being here bright and early. Our amazing keynote taught by Adam Sykulski. So we're very happy to welcome him here today. So Adam is an associate professor and reader in statistics at Imperial College London. He also obtained his PhD from Imperial College back in 2011. After that, he held postdocs at UCL and here in the US at the Northwest Research Associates. After that, he got back to the UK and he joined Lancaster University as lecturer. And from there, he moved to Imperial back in 2022. So his research focuses on time series and spatio-temporal statistics, especially with a focus on spectral methods. He's also deeply involved in various applications, especially in environmental, climate, and ocean sciences. I know that the work of his that I know best is his work on this ocean drifter data within the Global Drifter program. He's actually one of the few statisticians I meet at the ocean sciences meetings. So we have this shared interest in interesting and complex ocean data. So today we will hear about his latest work on spatio-temporal statistics. So that was the Debiased Spatio-temporal Inference. Take it away.
Yeah. Thank you so much, Mikhail. Thank you to Mikhail and Anne for organizing this workshop, and Jess as well, and others who have been involved putting this together. It's really great to be here. Thank you for giving me the early slot. I'm on UK time, which is in the afternoon. You would not want to see this talk at 4 p.m. if you gave me the late slot. That would be a mess. But I'm pretty sprightly now. I don't know about you guys. Thanks for coming. So yeah, I'm going to continue off on the same theme that Larry finished, insofar as this will be a neural net free talk. So this will be kind of classical statistics, spatio-temporal statistics in particular, joint work with some really great people around the world. Lockie that's Sydney, UNSW, EPFL in Switzerland, Jake and Sophia, Artur in London, Mike, who probably is the biggest owner of us at Amazon, and Jonathan Lilly. Some of you may know these great people. So I'm going to motivate my talk with a statement of the obvious, which is that spatio-temporal inference is hard, right? Any of you who do spatio-temporal know that it's hard. Why is it hard? I mean, others will claim this about other branches of statistics too. I'm not meaning to single this out in particular, but why is it hard? Well, we could develop a long list, and people have talked about that today in earlier days already, and will do in future talks today. Dependency, right? That's obviously the heart of it, which is that, we in Stats 101, we learn about IID, and then suddenly it's not IID at all. Of course, and then we have spatial heterogeneity, time series non-stationarity, spatial anisotropy, directional dependence, non-separability, that will come up today, that space and time cannot be separated in some multiplicative or additive marginal sense. So that's hard, right? So that's just the models. And then on top of that, we usually, in applications, get missing or irregular data, sparsely sampled, irregularly sampled, and spatially, usually in some irregular domain as well, with boundaries. That makes things hard. And then, of course, we have usually in applications multivariate data, which not only have all those challenges individually, but also they're usually collected on a different grid with different noise characteristics, different boundaries, etc. So that's really hard. And then, of course, others have talked about this. We learn Gaussian at school, and then things are non-Gaussian. And then we might start worrying about higher order interactions as well, although I won't talk about that today. And then on top of all of that, one thing that's key, obviously big in spatial stats in particular, sometimes time series too, are the computational demands of dealing with these issues. So that's obviously, hopefully, that others could probably add to this list. But this is my sort of frustrations, right? So then anyone who works in this area is very used to having to make trade-offs. These are necessary trade-offs to proceed, right? And a classic one might be computational speed versus statistical performance. We might have to trade one for the other because we just don't have enough time to achieve the statistical performance in terms of the processing or memory constraints that we're faced with. And then on top of that, we have the often arising in various forms is the classic bias variance trade-off. So for example, with non-stationarity, we might say, oh, okay, let's zoom in and assume local stationarity. So that can remove some of the bias because we're sort of saying, okay, it's more reasonable to say things are stationary locally, but if you zoom in too much, you run out of data and your variance blows up, right? So that's a classic example of where the bias variance trade-off comes up with non-stationarity. In all of these other issues, anisotropy, heterogeneity, missing data, these issues can come up to that you have some kind of bias variance trade-off that you're often having to optimize or trade-off in some sense, right? And I highlight bias because I'm going to talk about that primarily in this talk, but it's important to bring up these trade-offs because, you know, we're trading these things off, so we can't just ignore these other issues. Sometimes, and this is becoming a thing recently, big tech, use big resources to solve the first. So just, you know, buy lots of fancy clusters, GPU power, CPU power, whatever you want. And you can collect load, you can solve any problem with hammering with big data to solve the second trade-off, because asymptotically you're fine, maybe, if you have lots of data, and then computationally you're fine if you have lots of resources. As academics, these are luxuries we don't usually have. And even if you do have deep pockets, you don't always have the ability to just throw resource at a problem and solve it, right? Because you can't, there might be some kind of bias variance, there might be some aleatoric, irreducible uncertainty you can't reduce by just getting more and more data. So even if you do have that luxury, it often actually doesn't exist. So this talk, against that motivation, we're going to focus on some, when faced without these luxuries, we have to maybe not be lazy and think hard. Are there some bias reduction opportunities that we should use maths to take advantage of in spatiotemporal inference, but maybe more broadly, without compromising on variance or computational speed in those trade-offs? So can we sometimes reduce bias without having to do these trade-offs? And that's going to be part 2 of the talk. And hopefully I can convince you that there are such opportunities if we do some careful bias corrections of our methods without having to throw more resource. And that's part 2. But for 10 minutes before that, these techniques that we're going to use are going to employ some tricks from spectral and Fourier analysis. Hands up, who's here who's used some spectral or Fourier methods in their work before? Okay, that's pretty good. Show of hands. Often I get, blank stares. And so that's good. But for the benefit of everyone else, and as a reminder for you, part 1 is just going to be a very quick visual crash course in spectral analysis. It's going to be very quick, you'll see. But there might be something new for you spectral guys at the end of this crash course as we go into spatiotemporal. So I'm going to start with a time series. So let's just consider a basic sinusoid, e to t, a sine omega t plus psi. We have an amplitude, a phase, and an angular frequency that can represent this sinusoid that's evolving in time. It's a time series, right? A deterministic time series. Well, obviously, most time series don't look just like that. Usually, we can then represent more complicated functions as a sum of sinusoids. A sum of sinusoids at different frequencies, crucially where those phases and amplitudes are also frequency dependent. So where the sinusoids start can vary by frequency and how big they are. And then we stitch them together and we can form more interesting time series that may arise. This might be an ocean wave, for example. And in a nutshell, for those of you not done spectra before, look at those A's. Those are those amplitudes of those sinusoids, how big the blue curves are. Well, the power spectrum is really just the squares of the amplitudes, right? Intuitively, you're just taking the square of the amplitude at different frequencies and saying how big is it. So you're killing the phase information. You're saying you don't care where they start, you just care how big the sinusoids that create your overall time series are. And if it's stochastic, then this will live at all frequencies, right? So you'll have this spectrum. So that's what a power spectrum is once we go stochastic. But in a deterministic sense, we're just stitching sinusoids together, the idea of a Fourier transform, right? So that's just a very initial 101. But let's grow that now. This might be new for some people. Let's now consider a spatio-temporal sinusoid, e to t xy. So now we're bringing in two-dimensional space, and we're going to, and it looks like this. And the equation that's generating that beautiful wave is now a little bit more complicated because we've brought in something spatial. We brought in k, which is a wave number, and we brought in an angle phi, right? That wave is coming from and going to. And then we still have the stuff we saw before, where we have this frequency omega, and we have this angle psi as well, right? So this is spatio-temporal. We have a frequency wave number representation of a spatio-temporal sinusoid. And with ocean waves, in most applications, you think of k being a function of omega as well, right? So here you can get this kind of non-separability idea in space and time, that k will be a function of omega. So the sinusoid is specified by frequency and direction, right? So this is just the spatio-temporal extension of that one sinusoid in time, right? But in reality, we can think about more complex processes by adding lots of these together, right? So we've got lots of these different ones that are different at different omegas, and we could sum across them, sum across the different frequencies omega to now create a very choppy distribution. That might be a bit more realistic. For those of you who are surfers or sailors, you might, especially surfers, you might know about this happening. You might not go surfing in these conditions, but you would have, for example, wind waves and swell waves coming from different directions, right? Far-fetched and waves coming from large distances and short distances. So you would get these sort of different directions, different frequencies, different amplitudes adding together, right? So one option is to describe, this is the part that might be new to some people, the second order properties of this process using something called the frequency direction spectrum. So now your spectrum S is not just a function of frequency, it's also going to be a function of direction, phi. And a nice way to represent that is to split them. They're not fully separable, but we're going to have S omega, and then you're going to, which is the power spectral density. So you factor that out. And then you have this, what's called a spreading function, right? D omega phi, where your spreading function is going to tell you about at what frequency and angle waves are coming from. And then you determine the amplitudes with S. So the frequency direction spectrum therefore describes the variance contributed by sinusoids of different frequencies and directions, right? Make sense? Of course, this is still in a deterministic world. And this is what it might look like. These three sinusoids are just dots. Just like we had dots in that spectrum in one axis, now we have dots in this two-dimensional space in frequency and angle. But in reality, we'd expect this sort of spreading to happen, right? So these aren't going to be dots, but they're going to be kind of spread blobs, which is going to have like the wave isn't exactly, there's some stochasticity, it isn't exactly coming from one angle. So there's noise there. And you get this even noisier looking ocean. Notice that the z-axis is stretched here, right? So whilst this is kind of realistic data, it's not a realistic looking ocean like that. But if you recalibrate the axis, then it will. I'm sort of exaggerating the effect of the wave heights, but we can model wave heights this way, right? So this is just a little crash course to get you thinking about what are spectra. They're basically, telling you about frequency, or in spatio-temporal, sort of frequencies and directions and wave numbers and so on, by looking at where these concentrations are in these spectra that represent the signal in space-time. So against that little primer, I'm going to move to my talk, which is on debiased spatio-temporal inference, right? And we're going to go back and start with time series just to keep things simple. So let's just start with time series and let's keep things really simple to start, but these ideas extend more generally. Let's say we observe just a real valued stochastic process, xt, at integer times t. Let's assume it's zero mean. We make a lot of nice assumptions at first. Our regular data sampled every 1 point, and it's Gaussian, just to start things nicely. If it's second order stationary, which is also very nice when it is, we can define the autocovariance function to completely characterize all the dependency structure in the signal through gamma tau here, expectation of x with itself at some lag tau. Now, we could just end the talk here by specifying a parametric form for gamma, and we fit by a maximum likelihood or your other preferred method. And you can be done. But as we get to especially spatial data and large data, then maximum likelihood has some issues even with Gaussian because we have to invert these covariance matrices that was discussed by, I think it was a question by Brian. What was it, John, actually, did you say about this? Someone was saying about inverting large matrices in spatial data earlier this week. So that's a computational challenge, right? So we don't end the talk there and we think about how can we maybe speed things up. Well, this is where power spectral density techniques can be very useful. So what is the power spectral density more formally after I showed it to you visually? Well, it describes the distribution of power into sinusoidal frequency components that describe that signal. So under some assumptions of absolute summability of that autocovariance sequence, then this power spectral density exists and it forms a Fourier pair with the autocovariance. It's like flipping a coin with the autocovariance sequence. Fourier transform one to get the other, inverse Fourier transform to get it back. So we can equivalently describe this time series by autocovariance function or power spectral density. So nothing lost yet by thinking in a spectral sense. Okay, so far so good? Yeah, cool. So how do we estimate this in practice? Well, the simplest estimator is something called the periodogram, which is defined as such, which looks a little bit like what you might think a power spectral density estimate should. We're sort of taking a Fourier transform, we're squaring things to get those square amplitudes. We're dividing by our sample size. Turns out that estimator is actually the same thing as the Fourier transform of the biased sample autocovariance, which is what I'm calling gamma hat here. So this does give us something positive, as it should, but it's a biased estimate to F, right? Why is it biased? There's lots of reasons. You could think if this summation is over a finite sample size, it's causing this truncation that's happening, and you can see it from the last equation. That is a Fourier transform of a biased autocovariance. And this sort of triangle kernel is going to be important for bias correction in this talk, because here actually we know the bias, right? We know that this is kind of for time series 101, that if you take the expectation of your biased autocovariance, you're dividing your by n everywhere, but you have n minus tau pairs at lag tau because of the truncation. So you have this kind of triangle kernel bias, which is a problem, right? And it gets bigger as tau grows in a relative sense. So we know the bias, okay? But the periodogram is used in something, in inference, in something called the Whittle likelihood. So the Whittle likelihood is something that approximates the maximum likelihood of a Gaussian or even non-Gaussian time series and can be extended to a spatial-temporal setting. So for this talk, we need F, gamma, and I. These are the three things we need. So just as a reminder, F is the spectral density, gamma is the autocovariance, and I is our estimate of the spectral density called the periodogram. So we need F, gamma, and I. These are the only three things you need in your head for this talk, because we can combine them in clever ways. So the Whittle likelihood combines them by taking doing parametric inference by saying you have some spectral density f, which is a function of omega, and some theta you wish to estimate. And you're going to estimate that by maximizing this likelihood, this pseudo likelihood, which contains this density, but also contains the data through the periodogram. So the periodogram is your estimate to the density, and your model is your spectral density function. So you combine them in this way, and it's a nice half-page proof. You can set a student to show why this approximates the maximum likelihood. In the IID case, it's exact. And we sum over these, I'm going to say in inverted commas, independent frequencies, because they're only independent asymptotically. People often ignore that, but it's one of the sources of the reasons why it's a pseudo likelihood, because they're not really independent. And we maximize to get your theta, right? And what's nice about the Whittle likelihood, this is from the 50s. So this is a really old method, but it's still used a lot in spatio-temporal statistics, is because it's fast, right? And it's surprisingly good for a lot of applications. That I is just computed as on the previous slide via a fast Fourier transform. You don't need to invert any matrices, right? So it's just a fast Fourier transform here once, plug it in, and then you can use your favorite optimizer, just numerical, or you can put in the gradients, you calculate the derivatives, whatever you want. It's very, very quick, right? And you get your theta in no time at all. But it's using this periodogram, which is biased. And there was a Tukey quote earlier about the best thing about being a statistician is you get to play in everyone's backyard. I'm going to give you a different Tukey quote, which is more lives have been lost looking at the periodogram than by any other action involving time series. Right. He had a tendency to be dramatic. I don't know whether he means actual lives or sort of academic lives wasted. But yeah, so the periodogram is problematic because of this bias, right? So this bias translates to bias in your estimates. And this has been shown in a lot of literature over the last 20, 30 years, that the Whittle likelihood, although fast, often good, sometimes it's really not good, your estimates will be pretty biased, right? So you know, think of the periodogram as your enemy here. It's the problem, but you want to somehow make it work. Well, one option is you could correct the bias in the data, in the periodogram. So bias correct I. Why use something biased that's then going to translate to biased inference? And there's lots of work here over the last, this is all sort of really coming out of Bell Labs and all the great signal processing done over the last 50 years, that you can do all of these bias corrections. So on the left, here's an example of why the periodogram is biased. This is an AR4 process. You see it's biased. The periodogram, especially at high frequencies, is really overestimating the spectral density, right? And you can do a lot of techniques. Some of you may have seen these, like multi-tapering, Welch's method, lag windows, pick your favorite. There's a great book by Percival and Walden that describes these all. And you can sort of bias correct. This is a multi-taper estimate from an AR4. And now you can see that it improves things, but it does improve things at a cost. Whenever you reduce bias, you're going to end up increasing variance. This is the trade-off, right? And the reason why is because here you can see this is now sort of nice and independent, pseudo-independent between frequencies. Here we're kind of creating a smoothing artifact, right? So, okay, you're going to bias correct, but you're effectively summing over fewer omegas, true omegas. You're going to bump up the variance. It's like reducing your sample size a little bit. So this is kind of like running away from your enemy, right? Periodogram's your enemy and you're running away from it by trying to correct it. But what about we don't work on I, we embrace your enemy, you know its weakness, and actually move the model in the direction of the biased data, because you know what's causing the bias. This is where you stop and think. So you have this F that Whittle proposed that we put here, which you fit to I, but I is a biased estimator of F. But we know mathematically how much it might be biased by. So what we say is replace F with F tilde. F tilde is the expected periodogram, right? It's what we'd expect I to be for a given theta and for a given sample size. It's dependent on n, because the amount of bias is dependent. Eventually, it goes away. But for a finite n, it's going to be there. So dependent on n, dependent on theta. And how do you compute the expected periodogram? Well, it turns out this triangle kernel that I showed you earlier features back in, but we're going to have to take a Fourier transform of it. So we can say, well, the periodogram has this bias with the autocovariance, sample autocovariance, and we've got to Fourier transform it and set things just right. And we can compute the expected periodogram using another Fourier transform. Still no matrix inversion. So instead of one Fourier transform, we need two. So we argue that's worth it computationally. There's always trade-offs. So we remove bias. We haven't increased variance this time. We've increased computation a bit. But we think that's worth it. FFT is n log n. But crucially, by putting this in, we haven't increased variance because we're still summing over n pseudo-independent frequencies. We haven't done any smoothing to kill the bias. So instead of increasing variance, we've just increased computation a bit by moving the model in the direction of the data. And that's sort of the message of this talk, which is if you know your enemy, you know how they're biased, code it in, rather than trying to remove it from the data. So in a nutshell, fit the red line to your data rather than the blue line. So the red line is the expected periodogram. The yellow line is the periodogram. Blue is your spectral density. Okay. So we can do this in space as well. So I showed it to you in time because it's easier. But we can extend all of these models to space and space-time. So debiasing in space, for example, this is a Materne process sampled in France. My collaborator Arthur is French, so he liked to do things on France. Nice irregular boundary. And what he's showing here on the right in this animation, in this figure, is the expected periodogram. So we'd have a periodogram, and under expectation, all these ripples are actually encoding the bias, this time coming from the boundary. So you get a lot of bias in the periodogram from the boundary, and it creates these ripples. So this is now something that we can use rather than just having a smoothly decaying spectral density as you have with the Materne. We fit this ripply expected periodogram and get much better results. Missing data as well. I told you that was one of the challenges. So if we just sample like on these rings, a Materne, then you get this ringing effect in your periodogram, right? That ringing moves into your data. So this is now the model. This is the expected periodogram. We can add that ringing effect back in, right? And I won't show you the equations to spare you that, but we can bring that in. So this can really make a difference. So some real data, not ocean, but the topography of Venus, the actual data is in the top left. And what we're doing is we're going to be fitting Maternes and simulating random fields from a Materne using parameters estimated as indicated. In the top right is our proposed method, the debiased Whittle. And what you see is that even though we're not matching the red and the blue, we are matching the smoothness and the range, the spatial ranges, as shown in the top left. But in the bottom methods, when you use Whittle, or even with tapered Whittle, so the alternative of trying to remove bias, actually what happens is things go really wrong, and you end up getting the wrong parameters, and you might think you have the wrong model. But actually, arguably, you don't have the wrong model, you just have the wrong parameters because they were biased, right? So it's halfway through the talk, so I'll pause for a few questions in the middle. Well, let me sip my coffee for a bit. Any questions at this point?
Maybe this is a too simple question, but in the time series context, like if you guys could write down the bias, like why can you just not correct for it? Like why not just divide by that factor and then you have something that's unbiased? Like is that somehow too simplistic, or like what's the bias?
Well, yeah. So it's a good question. But ultimately, it's the parameters that are biased, right? So we have this is in effect what we're kind of doing by putting this in, but we're trying to debias theta here, right? So we don't know exactly how theta is going to be biased, so we can't just do a correction afterwards. That's what this computation is all about. But yeah, at the heart of it, you're bias correcting something inside which is biased, right?
So this is basically equivalent to saying that, like, in this first equation, like, just effectively, I guess divide the I by this.
Okay. So I think I understand your question better now. So here we're moving the model to the data. Why not remove the bias from the data?
Yeah.
So the issue with that, if we go back to these equations for anyone who's done sort of time series, so why not put the unbiased in here rather than the biased? So but the problem is that actually this will end up being negative often, which it shouldn't be. Because the unbiased estimator is not guaranteed to be positive semi-definite, whereas the biased one is.
I see. And actually, I think one thing I didn't realize, it is on the gamma, not on the I. So
exactly.
On the bias in I.
Yeah. You've still got a computer.
Okay, I see.
Yeah. Okay. Some people have worked with putting the unbiased one in here. But the problem is that that spectral densities need to be positive, their densities, and it won't be in practice. Thing. So and also it's for the same reasons people don't like using the unbiased one. It's very variable as well, so you get very high variance. So again, trading bias for variance, right? So the argument in some sense is this is good except for the bias. So we want to retain its good properties and then we confront its bad properties by doing a model correction rather than a data correction. That's the argument I'm making here. I'm not saying, it's just something to think about. It's sort of coming at it from both ends. So you might work on this idea of here correcting bias in the data or your summary from your data, or you can think about moving your model in the direction of your data. And sometimes that approach ends up being the right one. That's what I'm kind of arguing here. Okay. So that was parametric inference. For the second part of the talk, I want to talk a bit about, and just extending this to a non-parametric approach, and I want to talk about space-time as well at the end. So in a non-parametric approach, I'm going to focus on something called Welch's method, or sometimes known as weighted overlapping segment averaging. Anyone here used this before? Calculating spectra? It's popular in astrophysics and popular in medicine as well, like EEG signals and so on. And the idea is like it's a very simple way of reducing variance in the periodogram by taking overlapping segments and averaging them. Right. So this is bias variance trade-off in action. That rather than taking a periodogram of your whole series, you take segments, overlap them a bit. To optimize that, and you end up with this I bar L, really simple. So it's the same I as before, and we're just dividing by segments. So this is a method from, this paper has like 20,000 citations, and those are old citations, so they count more. Yeah, we had a lot of like 70,000 citation papers yesterday. This is like 20,000 from paper from the 60s. So yeah, this one stood the test of time. So yeah, a motivating data example, just to mix things up, is some wave data. So here we've got two types of wave measurements at the same location from different types of sensors, acoustic and pressure sensors. So these are two different ways of measuring wave height. So you're going to have sea surface height on the y-axis and time on the x-axis. And if we apply Welch's method to this data to look at the spectrum versus the periodogram, so the periodogram is in faded yellow and Welch's method is in yellow, then we see a nice kind of peak in the spectrum at frequency just below 0.1 hertz. So these are sort of waves that are every 10 seconds, slightly more. And a decay in the spectrum, but maybe we're getting some increased bias in the tail, or maybe not. I'm leaving that open for now. You can judge for yourself later. For finite samples, the thing about Welch's method is if we want to decrease our estimator variance, smooth out this line, then we require the number of blocks M to increase and thus L to decrease the length of our blocks. Classic, right? But decreasing L will lead to increased bias because we have these bias issues that occur with the periodogram when the sample size is small. They're bigger when the sample size is small. So this actually means you become increasingly certain in an estimate that is increasingly biased. So you just get increasingly wrong with Welch's method. And this is kind of the argument we made in our paper, which is maybe Welch's method needs a bit of revision to address this bias issue, because we can correct it in the same way as I just showed you. But to do that, it's a little bit more complicated because we're in the non-parametric setting, so we need a non-parametric model. This is a choice. We could replace it with a different model. But if we just start with the simplest, we could just use rectangular bases and just sum it over rectangles like a Riemann sum to represent our spectral density. And we could just solve, this is our model, we could just solve similar to the parametric case I just showed you, that we could estimate these parameters AI. And how might we do that? Well, the corresponding ACF to each basis. So we're thinking about moving our model in the direction of the data. So we have these basis functions, which are our model, but we actually compute the autocovariance of those deterministic bases to get this row. And then this triangle kernel that I've been talking about appears again, and we can create these B tildes, which are going to encode our bias, right? So then we can end up with this F tilde that I showed you before, which is going to have these biased bases, which encode the bias in the data. So same idea as before, B were our rectangles, but now we're kind of creating these rectangles with these kind of beautiful decays, because this kind of smearing effect of the bias, we can encode it into our model. And this is our non-parametric model, but we're going to be replacing it with its sort of biased alternative. We're going to move it in the direction of the data. How do we optimize? Well, there's too many parameters. A1, I mean, this is non-parametric, so there's too many parameters to plug that in and optimize A1 to AN in the Whittle likelihood, because it's a numerical optimizer. It's not going to work. So instead, here we had to take some practical choices. We use the central limit theorem to appear to a more feasible weighted least squares solution, where we want to weight by the variability of Welch's estimator at different frequencies. But there's a problem here that we don't know the weights because it's dependent on the thing we're trying to estimate, F. So there's a kind of circularity problem here. But otherwise, we'd be fine. We can just use CLT. But some asymptotic theory saves us. So the main theoretical results of this work were just some theorems. I'll spare you the proofs, you'll be pleased to know, where we can kind of argue that in the limit, as things grow in terms of M and L, our number of blocks and their length, and this trade-off is interesting because M and L grow at different rates, we can replace something we don't know with something that we do know, which is just the value of Welch's estimator at different frequencies, which the square of which roughly approximates the variance. So anyone who does spectral stuff will roughly know that the square of a spectral estimate itself roughly approximates its variance. It's sort of a chi-squared type result. And then the solution is analytical. So if we go back to this motivating data, basically now we had this acoustic and pressure data. Well, they're actually a little bit different because of the way the data is collected. Spatial statistics is never easy in time series, but we have these two spectra which are a little bit different, but there's actually they differ due to something we know about, this attenuation, this red curve, right? So the acoustic measurement is attenuated. So we expect it to be lower at high frequencies. We'll just multiply by this function, this red function here, and that relates the two. Okay, so we know how they should be related. So now if we apply debiased Welch's estimate, this is the figure I showed you before on the left. On the right is a new figure using our method. You can see that we've been able to maybe go further into the tails and reduce some of this bias at high frequencies that was there before in both the periodogram and Welch's method. So Welch's method was pushing it up, but we've kind of pushed it down, right? And to show that that does a good job, well, with Welch's estimate, if we reverse the attenuation now, you'll see that things start to depart between the two spectra up until we reach some point at which they no longer agree, whereas now we can make them agree with each other, right? So this is kind of this bias correction in action that wasn't there before. So the acoustic and pressure sensors agree. So recovering this signal was important. In effect, we've kind of lowered the noise floor. People might have thought this was a noise floor, but actually this was increased bias, we argue. And the noise floor is actually quite a few decibels lower, maybe 20 decibels lower. So simulations, we have many. This is an AR4. We worked with AR4s before. And apologies for the change in name, but P Welch, just because that's the R name, is Welch's method. And you have this classic bias variance trade-off between, for a fixed N, how you set L with respect to N. So L is the length of your segments. So if they become short, you have bias domination. If they become long, you reduce the number of segments and you have variance domination. So you have a U-shape bias variance trade-off. But then our argument is, in this case, we knew the bias, we can almost remove it, right? And that's really useful, not only because then have we removed the bias, but then you can give some back to variance. So you've changed the bias variance trade-off. Now, up until a point, you can move along this axis and start killing variance, right? So when you can remove bias, you can then also use that to remove variance if you want. Okay. So I wanted to show you a few spatiotemporal plots to finish the talk. So going multivariate and spatiotemporal, this is a simulation of a wave buoy in the ocean measuring wave height in Z, but these are usually tied to the ocean floor. They also move in X and Y. Things in the ocean don't just stay in one spot. They either drift, or if they're tied to the ocean floor, they'll also move a bit in X and Y. So this is a wave buoy. And you can see, in essence, it's estimating 3 time series, X, Y, and Z over time. So actually, it's a multivariate time series representing a spatiotemporal phenomena. Okay. And as a reminder, before we had these frequency direction spectra that we were interested in, and we might try and estimate those from this buoy data. So people might want to estimate what these spectra look like to represent an actual wave field from a very sparsely sampled instrument. So from one instrument, you want to try and infer this. Okay. So how do people do spatiotemporal inference for waves, and how might we debias? So oceanographers have proposed lots of models for these frequency direction spectra. That's what S omega phi is, as a function of some theta that we want to estimate. But in practice, we only record the series X, Y, and Z. Ricardo talked a bit about this yesterday about Lagrangian data. So this is Lagrangian data. In practice, we're just observing this three-dimensional trajectory this time, right? Space-time. I think you were looking at 2D. Yeah. So in practice, we only record the series X, Y, and Z, and we want to estimate theta. So the current approach is to try to estimate S hat, some estimator of the frequency direction spectra, from X, Y, and Z. So you convert your data to some estimate of the frequency direction spectra, and then you use some kind of curve fitting to fit S hat to S, right? And this is the industry standard at the moment. But our approach, again, with this debiasing in mind, is you have a model, and under linear wave theory, you can convert the frequency direction model to a model for the data, which this bold S represents the multivariate spectral density F, the model for it. So you can convert that way, and then you do this quasi-likelihood inference, specifically the debiased Whittle likelihood, on this directly from the data. So just so I can show you that, basically these frequency direction spectra, imagine they're changing. In this case, the wave is just changing direction. then what will happen is these multivariate spectra, X, Y, and Z, will start trading off each other in different ways. So we convert this is a model, we convert it to that, and then we look at what the data is doing in multivariate spectral space, and we debias and fit that way, right? So again, it's moving the model into how the data is being collected. And I don't have more slides just because I didn't want to overload this talk. But what I did want to show, can I still talk for another 5-6 minutes? Yeah. I'll leave time for questions, is a little bonus. Because I wanted to, for those of you who hate spectra and Fourier, I wanted to do some debiased inference where no Fourier transforms are required, just to show you that this might extend beyond. This is going to be a different debiasing. And I want to ask you about, I can't resist but talk a little bit about drifters. As Mikhail said before, I have to add them in the end of my talk. So first I want to ask you a general question. If we have 2 points in the ocean, what is the most likely path that a particle of water at the surface might take to connect A to B or B to A? If you were a flat Earth conspiracist, you might say A to the straight line. If at least you acknowledge the world is round, then you might take the geodesic line. That might be a better start, right? A better null model, right? But even that, it's probably not the geodesic, because a particle of water from A to B is probably going to take the equatorial current and the Brazil current over the top, and B to A will be asymmetric, probably loop round the gyre, take the South Atlantic current up the Benguela current back to A. So we have this asymmetry, right? And the reason we studied this problem is a bunch of biologists came to us and asked us how these points in the ocean might all be connected, because this was at the Tara Oceans mission, which went all around the world, collecting genomic data about plankton at each of these locations, and they wanted to know about genomic diversity between the plankton at these locations. And they were very interested in the true distances between those locations, not just the geodesic distance, because that could affect genomic diversity. So use drifters. For those of you who've not seen drifters before, that's a drifter. This one's not tied to the bottom of the ocean. They're released in the ocean and they freely float. They mimic a particle of water. And in this animation, you'll see the Global Drifter Program, which is a collection of drifters since the 1979. Over time, they've populated them, so they have this global coverage now. And these drifters whiz around, and we have this is a Lagrangian data, just like Ricardo talked about yesterday, sampling the ocean in space-time in a very unique trajectory way. So we have this spatio-temporal slices of the true state of the ocean. And we can use this data to try and connect all of these locations in the ocean to determine their true distance and true connectivity. So to do that, we're going to find the most likely path. And I can explain this without equations, because all of you can follow this, hopefully. So we're going to start, this is a standard technique. We didn't come up with this first bit. You divide the ocean into bins to form Markov transition matrices, so Markov chains. So you're going to have a transition probability based on drifter locations from one time step to the next. And you're going to say it's a Markov chain in space-time. But a key parameter, of course, is Markov. You've got to select some time step. It should be chosen such that the drifter motions decolorate. They forget their history and obey this Markov property. And actually, it's not too bad. The drifter forgets its memory after about 5 days. That seems 2 to 10 days is the argument in the literature. In agreement with that, we set it at 5 days. It's not exactly Markov, but we proceed. Then the most likely path between any two locations, for those of you who've seen this kind of stuff before, can be found by any number of pathfinding algorithms in the literature, and we use Dijkstra's algorithms, the good old school computational statistics, to find the path between 2 points in the ocean. But we propose a key innovation, and this is the debiasing I want to talk about, which is actually we use Uber's H3 index. Anyone seen or used this before? To tessellate the globe. So standard approaches would use lat-lon binning. So you bin in what you think are squares, but aren't really. And there are two key advantages to using H3. So H3 uses hexagons and pentagons. It's a bit like how a football, an English football, is stitched together. And they use pentagons and hexagons. And one of the key advantages in this tessellation, each hexagon and pentagon is approximately equal area, unlike standard degree binning. So you really mess things up as you go towards the poles if you divide into squares, what you think are squares, because they're not. But actually, there's an even interesting, bigger geometric advantage for Markov chains, is that each polygon, if you look, shares an edge and two vertices with a neighbor. Unlike standard degree binning, for those of you who've done spatial statistics, you know you have this queen-rook problem, where, like in chess, where with a rook-type neighbor, vertical or horizontal, you do share an edge and two vertices. But with the diagonals, you share no edge and one vertex, right? So it creates this kind of skewed neighborhood relationship. And it turns out hexagons are kind of cool, that you can avoid that. And what that means is we can get these nice pathways. So these are the pathways I talked about using Dijkstra's algorithm. We can connect these points in the ocean. Blue is the lower number to the higher number, and red is the higher number to the lower number. So it's asymmetric. We know how long it takes, what path it takes to connect these points in the ocean. And if I compare that with lat-lon tessellation, so the first two are H3 grids, the last three are lat-lon grids. If you look at the lat-lon grids, they have a preference for making rook-like moves, right? You can see that especially in this one. It's just saying it's going in a straight line, right? Which is that's not what ocean currents do, right? They meander. So there's this bias coming in here. You can see it here too. Whereas I'm not saying hexagons are perfect. This is a tough problem. We don't have that much drifter data, but we can get more meandering type pathways. So H3 produces these more realistic trajectories. And then to embrace uncertainty, we can do most likely paths by doing, various uncertainty techniques, bootstrapping, rotations of the grid, etc. And you can find secondary pathways and really cool alternative ways the ocean might be connected, right? And this turned out to be the biologists, this made its way into their paper as well as our paper. They used all of these estimates to connect plankton in the ocean and found it to be much better than geodesic distance. To explain, because the idea is if there's a current dividing 2 points, then the biology of the plankton will be very different because it's hard for them to connect. It takes ages. But if there's a current linking them, like 1 to 2, then you will get strong relationships. So it's kind of warping space based on the currents using these techniques. And we can connect the whole ocean. So if we start at this red point, you can see it will take up to 8 years maximum for a particle of water to potentially visit any other part of the ocean. So obviously it's quite likely to sample the Atlantic and the Indian Ocean. It will take longer to get to the Pacific. It will take perhaps the longest to get to Alaska, which kind of makes sense. So you can connect. It's one ocean. You can connect the whole globe using these techniques. And this method, if you like this tool and you think it might be useful for your research, it's up on the NOAA website. So Mike, who's now at Amazon, unsurprisingly, is a great programmer. So he built these skills in his PhD, and he built this tool where you can plug in any coordinates. And the idea is that for those of you who are interested, how do you make this computationally realistic? You only have to wait a fraction of a second to get each path. So he loads the transition matrix into NOAA's computer, and it runs Dijkstra's algorithm just like that once you put the coordinates in. Because it would take too much storage to store the paths, right? There's so many options here. This is n to the 4, and we want some scale, so that's going to blow up. So instead, you just solve the transition matrices, which are n squared, right, rather than n to the 4, and you run Dijkstra's algorithm on the fly within NOAA's code. They don't know they're doing that. But we gave them the code, and they just put it up, and you can get these pathways really quick. So that's just a little bonus at the end. I just want to finish with some references on the earlier Fourier stuff. So it's in a string of biometrica papers, right? Why write one biometrica paper when you can write 3? So that's what we went with here to divide this up into parametric, non-parametric, etc. And then, because we like British journals, after Biometrica, we've also published two in JRSS on the spatial stuff, spatial and spatio-temporal for waves. And then finally, some code. We finally got around to putting a Python package up. If you're interested in these techniques, it's in the Journal of Open Source Software. So yeah, thank you very much.